Hello, in this video I'm going to go over an OCR mechanics question from the 2019 paper. It was quite a challenging question. It was the last question on the paper and it caused some problems at the time, probably a little bit unorthodox, not as bad as all that, but in the time constraint it's understandable that it did cause such problems. Anyway, it's about a uniform ladder that's resting along a wall, kind of unusually in this sense, like resting on top of it as shown in the diagram. And we're told it's uniform, and it's of mass m, so the weight is mg. Let's just change the colour of that. So that's mg. And there's another weight placed at a point C, which is a distance d from the bottom of the ladder, which is on ground A, and the weight placed there is 2 mg. The object is 2 mg. We're told it's smooth at some point somewhere. Definitely told it's smooth somewhere in the question, between the ladder and the wall. Yeah, that's smooth there. And we're told that it's rough somewhere as being rough at this point here. So just labelling the forces, let's call the normal contact force R there between the floor and the ground. Let's call the frictional contact force as F. This normal contact force on top of the ladder there is S. And let's mark on some angles, maybe mark this angle up as 30 degrees because we're going to need that for our resolving equation. Now the first bit is lots of stuff in here which is about it was an expression for this contact force S there. Now because there's a lot of distances involved in that, it must involve a moments equation for that, and the most obvious place to take moments about is A. I don't think we need any resolving, but that's going to be part B where we're doing that. So let's just do moments about A. We need I'm going to mark on some distances here. First of all, the perpendicular distance to the S force is here. Now we're told that the height of the wall is h. So we can do trigonometry because this is like the hypotenuse of the triangle here. It's a hypotenuse of that, so that's h over sine 30. Now sine 30 is a half, so it's going to be equal to 2h, but just mark it like that as h sine 30 for the time being. So the other perpendicular distances are this perpendicular distance to the 2 mg weight there. Now that is going to be equal to d cos 30. And similarly, because the length of the ladder is 2a, so the centre of mass is a along, this length here is going to be a cos 30. So that should enable us to get a moments equation. First of all, this one here is going anti-clockwise, so that's S times by h over sine 30. Okay, S over h times sine 30, and these both are going in the opposite sense. They're both going clockwise about A. So we've got minus mg times by A cos 30. And we've got minus 2mg times by d cos 30. Hopefully that will get to this expression, but I think we're going to have to do we're going to have to show that it is. We can't just write the expression out. Well, as I just said, sine 30 is a half, so this bit here is 2h times s. Let's take both of these over to the other side. So this is mga, the square root of 3 over 2. And this is 2mg d, the square root of 3 over 2. Beginning to see that this might be coming out now, often have that feeling. But I think we need an intermediate step yet. 2hs, we can take mg out as a factor, and also the square root of 3, and also the 2. And we're just left with a plus 2d And we can readily see now this expression is there. So we've done it. Let's write it out exactly as it is in the paper. So there we go. 4 marks for that, setting up the equation and then rearranging. So we got that. Not as bad as it looked, as I say. Okay, let's make up a bit of space for part B. Now part B talks about it being in limiting equilibrium. So we know that F is equal to mu r. So we know that F is equal to 1/8 the square root of 3r. It's always worth writing that down, even if you know nothing else, because often there's a very easy mark just for writing that down. So that's F. Now, what to do here? Well, 7 marks. So if we can get S in a different kind of resolving type approach, which we should do now, because we know what we know what the F is in terms of R. So resolving vertically and horizontally, we should be able to get S again and then equate it to that and get what we need. So I'm going to resolve vertically and horizontally here. So resolving vertically, well, I've got the component of the S, that's S cos 30. The component of this force vertically is S cos 30. That's going upwards. Going downwards is, oh, also the R is going upwards, of course. And then that's been counterbalanced by the 2mg and the mg. Okay, so we've got S, the square root of 3 over 2 plus R equals 3mg. Let's leave that there for the moment. And then we can resolve horizontally. We have horizontally, we've got the component of S, that's S sine 30, horizontally. And we've got that counteracting with the F, which we know is equal to 1/8 or 1/8 the square root of 3r. So we've got S times by half is equal to 1/8 the square root of 3r. Right, so we can substitute for r in either of these expressions. Let's just write r from here equals to, so I do it that way. Let's write r, let's substitute r from the other side. So we've got r from here equals to 3mg minus the square root of 3 over 2s. So we've got, let's tidy this up a bit as well. S is equal to 1/4 the square root of 3r. So let's substitute this r into there. So substitute r. We're going to get S equals to 1/4 the square root of 3mg minus the square root of 3 over 2s. Now multiplying that out, I'm going to get S is equal to 1/4 the square root of 3mg minus, and that's going to be 3 over 8s, because square root of 3 times by the square root of 3 is 3, 4 times 2 is 8. Taking this over to the other side, I'm going to get 11s over 8 is equal to 1/4 3 the square root of 3mg. Okay, and therefore I'm going to get S is equal to 6 over 11 square root of 3mg. So let's make a bit more space, but now I've got an expression for S here that I can quote with this expression for S here, and hopefully that it means I'm going to get where I want to be. So I've moved things around a bit. There's my part A that I've done. I've got an expression for S there in terms of the A, D and H, and I've got an expression of S here in terms of independent of A, D and H, both with mg in, so I can equate S. So I have mg A plus 2d, the square root of 3 over 4h equals to 6 over 11, the square root of 3 mg. Oh, clearly quite a bit of this stuff cancels, which is always a nice thing to see. The square root of 3 cancels. Obviously, so does the m, which it often does, and so does the g, which it often does. So we want an expression for h here, which is on the bottom there. I can then pretty well get h, kind of doing a bit of cross multiplication there. H, the 11 comes to the top, the 6 comes to the bottom, so that's 11 over 24 A plus 2D, which is what they asked, the form they wanted. They said it's in this form, so K equals to 11 over 24 in the form. So that's part B done. Okay, so we're getting there. That's the meaty part. We had to resolve horizontally, resolve vertically, and compare to our moments equation in part A. And then part C, now this is only a couple of marks, but it does require quite a bit of ingenuity and a bit of thought. Normally when we talk about greatest possible values of things, we're using the inequality f is less than or equal to mu r, but that's not applicable here. That's not relevant because we're already told it's in limit and equilibrium. So we need to think of some other constraint here. Well, if you look at it, we can see that h, obviously the ladder, the h bit there can't be bigger than this distance here. That distance there is equal to 2a sine 30. H can't possibly be bigger than that, otherwise it wouldn't be resting on the ladder. So that's the constraint we're going to use. So a bit of ingenuity needed there. So we have h is going to be less than or equal to 2a sine 30. And that means sine 30 is a half, so h is going to be less than or equal to a. And so we have 11 over 24 a plus 2d is going to be less than or equal to a. Multiplying out, I get 11 a plus 2d will be less than or equal to 24a. So 11a plus 22d less than or equal to 24a. So that gives us 22d. It's got to be less than or equal to 13a. So that gives us d is less than or equal to 13 over 22a. So that is that. That's virtually the question done, except as there often is, there's this kind of bonus mark almost, or an mark independent of anything else. Even if we've had no clue about anything else, we've still got the inevitable modelling improvement kind of question. State one improvement that could be made to the model. Well, look at the assumptions in the model is a good thing, and think, well, can we actually improve on that? There are various things that the rod is non-uniform. I might just, the most obvious one I would have thought is that the contact here is rough. So we could say, it's not the only possible answer, e.g. contact, model contact between ladder and wall. Between ladder and wall is rough. And wall is rough. And that will get it. What I would urge, I said there's other possible answers. You can refer to the fact that it might not be uniform. Also that this might not be a particle here, so consider that. Various things it could be would get the answer. But be careful not to list too many, or I would just list one that you think is likely to be correct, because if you start listing incorrect things, you will lose, you won't get any credit. And the classic one here is if someone says use a more accurate value of G. Well, we haven't even used the value of G in this question. It's independent of G. This final, all this stuff here, G cancelled. So that would not be on G cancelled from this bit as well, or cancelled. It's not, G is not, dependent on the value of G. So a more accurate value of G would not get the mark in this question. So even if you wrote a lot of correct stuff, like I've written here, and if you put something that's wrong, like more accurate G, you will not get the mark typically. So just write one thing that you think is likely to be correct on that. Okay, I hope you found this video useful. It's a relatively tough question, but hopefully you can see it's not quite as bad as it looks. It's easy to say that, when you've got plenty, all the time in the world to do it, of course. Okay, that's it. Bye.